In this segment, we are going to explore loan amortization or amortized loans. An amortized loan is the type of loan that requires equal payments. Therefore, we can think of payments as stream of annuities. So every payment is equal over a period of time. So this conforms to the description of an annuity. And as a result, the loan amount itself can be thought of as the present value of these annuities. While the payments are equal during the life of the loan, each payment includes varying amounts of interest and principal. Since at the initial periods of the loan, outstanding balance is large, a larger proportion of the payment is made up of interest payments. But as the outstanding balance declines, interest payments decline, and the larger proportion of the payment is composed of principal payments. In an amortized loan, last payment should bring the outstanding balance to zero. Let's explore this concept or the amortized loans through an example. Let's assume that a company borrows $1 million for 10 years at 12% interest. The loan will be paid back in 10 equal installments. For each of the 10 years, we will have to calculate the annual payment, and we will also decompose the payment into interest and principal. So this is very much in compliance with the description that we made earlier for the amortized loan. So there is a loan that is extended to a borrower. The amount is $1 million, and the borrower will make 10 payments over a 10-year period, one payment per year. And once the borrower makes the last payment, the balance will be drawn down to zero. So our charge in here is to calculate these annual payments or annuities in the amortized loan, and then we are going to decompose these payments into interest and principal components. So when we frame the loan problem as an annuity, the loan amount, as we mentioned, is equal to the present value of the annuity, and all of these equal installments will be the annuity in a present value of an annuity. So present value of the annuity is the nominal value of the loan, and the periodic payments, including principal and interest, are the annuities. So in our example, we have the present value of annuities as 1 million, which is equal to the nominal value of the loan that is made out or borrowed by the company. And this loan is going to be paid out over a 10-year period with equal payments when the interest rates are 12%. So if we use the present value in annuity formula, where we have on denominator 1 plus interest rate to the power n minus 1 divided by 1 plus interest rate to the power n times interest rate. So if you plug in the appropriate interest rate and time or length of loan or debt maturity values in here, we get 1 plus 12% expressed in decimals to the power 10 minus 1 divided by 1 plus, again 12% to the power 10 times interest itself, that is 12%. And this factor, which we call present value of an annuity interest factor, is equal to 5.65. So the annuities, that is the amount of payments that are going to be made times this factor, should be equal to 1 million. And then if you solve this for A, for the annuity, we get 1 million divided by 5.65, where the annuity itself is 176,984. So this means that the borrower is going to make 10 payments, each $176,984. So now we can decompose this $176,984 into interest and principal components, and every period the proportion of interest and principal naturally is going to change, because interest charged on the balance is going to change throughout the loan life. For instance, initially when we make the first payment, the outstanding balance is $1 million, and 12% of $1 million is going to be $120,000. So in the first payment that we make, $120,000 of $176,984 is the interest payment, and the remaining amount is the principal payment, which is the difference between $176,984 and $120,000, which is equal to $56,984. So principal payment in the first payment is $56,984. So this means that when we start the second period, the outstanding balance is going to decline by $56,984, and the interest now, the 12% now, is going to be charged on that remaining balance. This table shows all of these calculations. So again, the starting balance is $1 million. Each payment is composed of $176,984. In the first payment, $120,000 is the interest payment. Principal is the difference between payment and interest, which is equal to $56,984. Once we make this principal payment, the loan balance at the end of the first year declines to $943,016. So from period 1 to period 2, interest is going to be charged on this $943,016, which is equal to $113,162. We are still making the same amount of payment. This time, principal grows to $63,822, because the difference between $176,984 and $113,162 is equal to $63,822. So this is the second principal. Now, after payment of this amount, the loan balance is going to decline to $879,194. The interest from period 2 to period 3 is going to be charged on this balance. In this case, it is going to be $105,503. And in this case, again, since we are making $176,984 as the recurring payment, the principal that is paid increases to $71,481. And this brings down the principal to $807,713, and so on. So once we make the last payment, $176,984, the loan balance is $158,022, and the interest that is charged on this is $18,963. This means that last principal that we pay is $158,22. Once we make this payment, the loan balance draws down to zero. This is what we mean by after the last payment, loan balance being drawn down to zero. So last payment wiped off the existing balance, and now we don't owe anything else. So entire loan has been paid, the principal has been paid, as well as the interest payments were made during the same period. So the calculations are repeated in here, and this also shows the principal payments in the first and the second cases, just to clarify how these figures were derived. So this is a simple example of amortization, and we created a table in here to show that each payment included varying composition of interest and principal, and the loan balance decline in this fashion as it is shown in the last column. In Excel, we have a few useful functions that will help us to produce all of these figures. A function called payment will allow us to determine the equal installments that is needed to pay off an existing loan balance. In this example, the amount of loan was $1 million. So we will use this payment function to figure out the $176,984, which is the annual or equal installments. The arguments in the function are interest rate, which is 12%, number of periods, that is the maturity of the loan or the length of the loan, which is 10 years. Present value here represents the loan amount. In this case, we will use a minus figure. So 1 million is the loan amount, and then we will enter 0 here, which is the future value. This figure indicates that after the last payment, balance declines to 0. So if we for some reason want to leave some balance, we can change that to that number, and then we can recalculate the payment. But in a typical amortized loan, this future balance is always 0. And the type of the annuity is ordinary annuity. Therefore, we have a 0 in here, or we could leave it blank. It would still do the calculation and produce 176,984. So payment function calculates the equal installments. As long as we have the amount of the loan, interest rate, and the length of the loan or the maturity of the loan, we can produce payments very, very quickly in an Excel function. And then we have another useful function in Excel, which helps us to calculate the interest payment that is made in each of these periods. So in this function, the function is IPMT or interest payment. The arguments are interest rate. The second argument is the interest payment for the period. For instance, if you would like to find out the interest payment in period 1, we will need to enter 1. If you want to find out the interest payment in period 2, we need to enter period 2, and so on. So this figure that shows in red shows the interest payment for any specific period, whether it is 1, 3, 5, 8, 9, whichever period that we would like to calculate the interest payment, we enter that figure in there. Number of periods is the maturity of the loan, so that is always the same. That is, for each loan there is only one maturity, and then again the loan amount, which is 1 million, that also remains constant. So the only thing that changes in here is the period, which produces a different interest payment for each of these periods. So if we entered in here, let's say 5, the function would produce $87,318. Similarly, we have a principal payment function. The arguments are very much the same. We have this time interest rate again, and period that we want to calculate the principal for. Number of periods is the maturity of the loan, and the loan amount. So this function produces the principal for any given period. For instance, if you would like to calculate the principal that was paid in period 1, we would just enter 1 here for period, and that would produce $56,984. If we change this number to 5, the principal that is paid is 89,666, and this function is going to produce 89,666. So this is the Excel application or Excel tools that we need to construct an amortization table. You could replicate this by using these functions in an Excel sheet. Now, in this example, the payments that we made were annual. So in this loan, the company made annual payments at the end of each year. It is possible that loan arrangements may require more frequent payments. For instance, it is possible that we could make monthly payments instead of annual payments. If we needed to make monthly payments, there are a few changes that we need to make in calculation of the monthly payments. The interest rate will have to change, because now instead of making an annual interest payment of 12%, we are going to make an monthly interest payment of 12% divided by 12, that is equal to 1%. The number of payments in our original case were only 10, but since we are now making monthly payments, we are going to make 10 times 12, that is equal to 120 payments. So in the functions that we utilized before, for instance, in the payment function that we have shown in the previous slide, if we enter 1%, and instead of number of periods that we use 10, if we enter 120 and keep the other arguments the same, we will find out that the monthly payments would be $14,347. So if this were the case, we would make 120 $14,347 payments, where the total payment would be equal to $1,721,651. In our original case, we made 10 payments, each $176,984, so our total payment was $1,769,842. So in the original case, the interest that we paid on the loan, which is total payment minus the principal, is $769,842. If we make monthly payments instead of annual payments, the interest that is paid drops down to $721,651. This is happening because when we make monthly payments, we are drawing down the principal faster. As a result, the interest that is charged becomes smaller. So for instance, in this case, for an entire year after we make the first principal payment, for the entire year, we have a balance of $942,043,016. So one more time, in the case where we make monthly payments, we draw down the principal faster. As a result, the interest, the basis of interest, which is the outstanding balance, shrinks faster in this monthly payment scenario. As a result, we have a lower interest payment.